And yeah, let me just take a quick minute at the beginning to introduce Andrea Merloni, who is from MPE and is going to tell us all about eROSITA. Some of the more senior members of the department might actually remember Andrea, as he did his PhD at the IoA originally, before moving to Munich, where he's basically been ever since. There's a variety of different postdoctoral positions and fellowships spread across MPA, MPE, the Technical University, before landing the prestigious project scientist position for eROSITA. And as I said before, that's what he's going to tell us all about today. This is a new X-ray survey that's just recently been launched, so it should be very exciting. With that, I will hand straight over to you, Andrea. Take it away.
Thank you. Thank you, Dan. I really would love to be there, have some wine with you after this, but that's where we are. And I'm actually happy, I'm very happy that you gave me the opportunity to tell you about our new instrument, eROSITA. So the outline of my talk is straightforward. I will start with just a brief description of a bit of history and scientific drivers behind SRG and eROSITA, some technical characteristic and mission profile, and then dive into telling you a little bit more about what happened over the last 7 months, including some highlights from the early performance verification observation and the report on the status of the all-sky survey. So yeah, survey is the key word. It's a survey, X-ray survey instrument that we built, and surveys for astronomers can do many things, of course. You build large data set that you can use to do robust statistical inference on the population synthesis level. You can use survey to discover unusual and rare events. But of course, one of the things that survey do is to give you a map of your neighborhood. So this simple image of one of the first spectroscopic surveys in the 90s, this is a CFA spectroscopic surveys, revealed, for example, the filamentary nature of the large-scale structure. I think this had a very large impact, not just on astronomy, but I think even on humankind. So a more modern version of a redshift survey, and particularly one that is all-sky, is the 2-mass redshift survey showing here. And the reason why I'm showing that is this local survey of big galaxy allow you to probe not only the position, a three-dimensional position of galaxies, but also their motion, peculiar motion relative to the Hubble flow. So this is what you would need to infer the dynamics of the underlying dark matter. So you can use this as initial condition, put them in a computer, and people then build so-called hydrodynamical simulation, which are constrained to the local large-scale structure. And for example, in this computer simulation from Klaus-Dolag at LMU, then you can color your sky, you can put on, so to speak, your X-ray eyes. And so this is actually a map, reconstructed map on the computer of the hot gas that you would be able to see if you had X-ray eyes. And you know, if you want, simplistically, one of the motivation for building eROSITA was to turn this computer image into a real image. Of course, this is a local view of the large-scale structure, could be quite interesting, but the other thing we know in 50 years of X-ray astronomy, if you look at the patch of the blank X-ray sky, here on the bottom left simulated one, most of the sources you see are actually glowing black holes, but then you clearly see the diffuse X-ray emission coming from the largest collapsed structure in the universe, clusters of galaxies. And since the discovery of the accelerating expansion of the universe, it was realized by many, and here is a very simple illustration in this review by Rosati et al. In 2002, that just by simply counting quasar clusters as a function of redshift give you constraint on the equation of state of the universe, so the critical, the densities of the different components. So this plot just shows, as a function of redshift, the cumulative number of objects above a given mass normalized to the redshift 0 value. And you see how different the curves are for different cosmological parameters. So here, on one hand, you have X-rays which are sensitive to these large structures. These large structures live on the exponent decline of the dark matter halo mass distribution. So counting them is an exponentially sensitive probe of the growth of structure. And so this is in fact the main motivation, scientific motivation with which we went to the funding agencies. So the actual consolidation of the mission profile for eROSITA and SRG came in the early 2000s, when various papers, here I'm citing this quite influential white paper by Hamann et al., just quantified how many clusters do you need in order to put very stringent constraint on cosmological parameters, so-called stage 4 cosmological experiment. And it turned out that you need about 100,000 clusters. And so that's what have driven the design of the instrument. So you need a very sensitive instrument. You need to be sensitive in the energy range where these clusters emit, which is typically soft X-rays from a few hundreds of eV to 2-3 keV. And that the design came out, and the proposal was put together under the leadership of Günter Hasinger, at the time director of MPE, in 2006 to our German space agency DLR. And the proposal was approved for funding in 2007. And after an agreement with the Russian space agency Roscosmos, the mission called Spektrum-Roentgen-Gamma SRG with eROSITA on board was consolidated and approved in 2008 when building of the hardware started. So in Russia, SRG has an even longer history. There was a mission called Spectrum X in the late 80s. It was a pretty large X-ray a series of X-ray instruments, X-ray and gamma instruments, with large international participation, including UK, but this did not survive the funding crisis of the Russian space science after the collapse of the Soviet Union. And so it was only in the early 2000s that it was revived, and it became the Spektrum-Roentgen-Gamma as we know today, with eROSITA as its primary instrument and an hard X-ray telescope called ARTEC-C. And this was developed in Russia under the leadership of Rashid Sunyaev, and in Germany under the leadership of Peter Predel. So the German funding provide the resources to build the telescope, eROSITA. So as I said, Peter is the PI, and he shared with Paul Nandra, our director at MPE, most of mission level management. But the consortium of institutes that built the instrument is here listed. It's a few universities in Germany and a large series of industrial partners. The main characteristic of the management of eROSITA I want to emphasize here is the large role that MPE had as not only scientific institute and project management institute, but also in instrument design, manufacturing of most of the hardware. Indeed, we did the integration and the test of the integrated hardware in our premises, and now we are responsible for part of the operation, data handling, processing, and archive. So for a single institute, it's really a huge amount of effort. So it took about 12 years from mission adoption to launch. This is the picture of the rocket in Baikonur a few seconds after ignition. But before I move on, let me make a step back and tell you actually what we built in these 12 years. This is a picture taken in Baikonur just a few days before launch, and it shows without the protective cover the payload and the two instruments. eROSITA is the larger one here on top, and ARTEC-C is this slender black tube I will tell you about in a second. They both are co-aligned. They look at the same part of the sky at the same time, and they are mounted on this spacecraft called platform navigator platform. Here you see the solar panel. So all the communication with Earth happens on the platform. And these are now mounted in this picture. The payload is mounted on the upper stage that brought it into its L2 orbit, or in the orbit towards L2. So I said I would tell you something about the ARTEC-C telescope. This is actually the only slide I'm going to tell you. Main reason is this is a PI instrument, so I'm not participating, or at least only marginally in science, but it's interesting, I think, for you to know. This is a sort of a little sister of NuSTAR. It's a focusing telescope that works at energies, actually I think between 4 and 30 keV. With an effective area factor of maybe a couple smaller than NuSTAR. So in this effective area, on-axis effective area plot, the ARTEC-C curve is the red one, the NuSTAR is the green, and the eROSITA is the blue. And you see that at few kV, up to 10 kV, it's maybe less than a factor of 2 smaller than new star, but with quite good angular resolution, imaging capability, and also energy resolution and time resolution. But okay, let me tell you now more about eROSITA hardware. So these pictures were taken at MPE in the lab maybe 3 years ago, where we were completing the assembly of the telescope. It's an array of, it's not a single telescope, but actually an array of 7 identical telescopes that you see here on the left. They have a quite compact configuration. So the focal length is only 1.6 meters, which is much smaller, let's say, than Chandra and XMM. This helps you to get large field of view. But of course, the price you pay is the effective area at high energies, because high energetic X-ray need longer focal length to be focused. The mirrors are essentially the same technology of the XMM mirrors, and so they deliver very similar characteristics. So the angular resolution of half energy width is about 18 arcsecond on axis, and 26 arcsecond when you average over the entire field of view, which is what matters when you're scanning over a source in the sky. These correspond to basically positional source accuracy of about 3 to 5 arcsecond for point-like sources. And here you see an image of the PSF taken in our lab, that you see the typical degradation of the Volter X-ray mirrors as you move away from the central axis. And here you see effect of the color aberration due to different energies beyond the very nasty PSF degradation. But because we have so many data that we take in our lab, we can calibrate those effects quite accurately. One other thing to notice is that these mirrors have a baffle in front that have to be aligned to very high precision. And this is needed to prevent single reflection, essentially stray light effects that will introduce ghosts and strongly increase your background, which is critical. It's critical to reduce such a background if you want to detect low surface brightness diffuse emission. On the right, you see a picture of the focal plane with the 7-camera electronic box in gold. They operate the 7 cameras. The cameras are also an evolution of the XMM PN that has been very successfully in orbit for more than 20 years. And they're an evolution for a number of reasons. We have frame source, so no out-of-time events. There are no chip gaps, and they're very good uniformity and very little temperature dependence. So sorry, here you see kind of a flat fielding. So an image of one of the cameras, you see the entire camera is exposed, and the noise level is low and very uniform. So all these characteristics give us spectral resolution at all measured energy, which are almost a factor of 2 better than XMM. So under many points of view, these are probably the best CCD camera ever flew for X-ray astronomy. This is the main, technical characteristic of tell you how big the telescope is. So this is the field of view average effective area. So how big the photon collecting bucket is. The 7 eROSITA combined telescope is the red, and the XMM3 combined telescope is in blue. So between less than half kV to 2 kV, essentially eROSITA is as large as XMM. And much larger than what the Chandra is, especially now after the degradation of the soft response. Of course, the other advantage of eROSITA, we'll show in a minute, is a large field of view. So when instead of plotting the simple collecting area, you plot the grasp, which is essentially the product of that collecting area times your field of view. So it's an indication of how fast you can survey the sky of a given depth. So here you see that now we are a factor of 5 better than XMM Newton due to our large field of view, and a factor of 100 better than Chandra is today. So that's another way of showing almost the same thing, the size of the eROSITA field of view compared to XMM Newton, Chandra, and the full moon. The other characteristic that this plot is stressing is that we have introduced we have introduced a feature of observing mode that is not present in either Chandra or XMM Newton, which is a raster scan mode that allow you to go over rectangular patches of the sky of any given size that you want, up to 150 square degrees or something like that, using this raster scan mode in which the spacecraft goes back and forth, and you can adjust the speed, so adjusting the depth of your image. And so this is what you want if you're gonna get uniform exposure over a large portion of the sky. Now I'm showing you an animation of the operation mode of eROSITA. We are, as I told you, doing mostly scanning, and this is how the All-Sky Survey is operating right now. The telescope is in this large orbit around L2 that I will show you in a minute, and it moves slowly rotating and essentially covering great circles in the sky. The rotations are it takes about 4 hours to do one full rotation. So in a day, you have 6 rotations, and in this 6 rotations, the spacecraft advances by about 1/6 of the field of view, so which is 1 degree. And because the orbit of the L2 point around the Sun has 6 months periodic, by advancing by 1 degree, you cover the whole sky in exactly 6 months. And the plan is to do that for eight times, for 4 years, uninterrupted, hopefully, so that we can either compare 8 independent whole sky images or stack them and get to much deeper images. And this 4-year survey will be followed by at least 2.5 years of pointed observation, including time open for the community. So this is the classical figure of merit for the surveys that eROSITA is going to do. Let's focus on the left-hand side. That's the point source sensitivity. So on the x-axis is the area of the sky that you cover. On the y-axis, the flux limit of the sources you can detect. On the very top right, there is a ROSAT whole sky survey, the only predecessor of eROSITA in terms of imaging X-ray whole sky surveys. And so over the first whole sky survey we are doing right now, we are improving over the ROSAT whole sky survey by a factor of a few already. And our plan, if we combine all 8 whole sky survey that we do in 4 years, is to go a factor of 20 or 30 better than the ROSAT whole sky survey over the whole sky. And then, of course, you go deeper around the ecliptic poles where all these great circles intersect. That's why you have this deep point at around 100 square degree or so. The number you want to remember is the sensitivity in the soft band between 0.5 and 2 kV of 10 to the minus 14 Hertz per second per centimeter square, which is our goal for the whole sky survey. So the main, I told you, the main motivation scientifically was to detect enough clusters, okay? I described you the characteristic of the instrument, and these are, of course, designed based on this simple plot that shows the extent of a cluster, the size of a cluster, mainly actually of the R500, the region in a cluster where the density of the ICM equal 500 times the critical density of the universe. And this is, green curves represent dark matter halos of 10 to the 13, 10 to the 14, or 10 to the 15 solar masses as a function of redshift. And this is their angular size. So, and this one arc minute red line is what we think we can safely resolve with our PSF, which, as I told you, has a full width of maximum of maybe 10 to 15 arc seconds. Okay, so this essentially tells you, this plot, that clusters more massive than a few times 10 to the 14, we can resolve them up to redshift 1. And we have then the sensitivity that I show you in the other plot matched to our knowledge of the cluster number density, predict that we should detect about 110, maybe 140,000 clusters with more than 50 counts in 4 years of survey. And this essentially amount to all massive clusters, all clusters more massive than 2 times 10 to the 14 that lie along our past light cone. These are some simulation that we did, extensive simulation that are based on n-body simulation, on which we paint galaxy, AGN, and clusters using abundance matching technique. And then we predict their X-ray luminosity, and we fold the predicted X-ray photon coming from the sky through the eROSITA response, doing a really end-to-end instrument simulation, which is very useful now for us to test our data flow, our pipelines, and in the future, our cosmology measurements. And I invite you to read this nice paper by Joan Comparat that describe the simulation themselves. But the nice thing that you can see, so this red point represents what we predict we will be able to detect as clusters in this wedge, ranging up to redshift 0.7, and in blue, AGN. And we will be able, in fact, once placed that in the 3D positions, to trace the large-scale structure really using X-rays. So a survey which is a factor of more than 1 order of magnitude improvement on anything done in the past, in many aspects, including spectroscopy, for example, of course, is endowed with tremendous legacy value. Beyond this large number of clusters, we expect to detect more than 3 million AGN, their typical redshift around 1, and typical X-ray luminosity of 10 to the 44 Hertz per second. But of course, passing over the galaxy, we will be sampling in large numbers the compact object population of the Milky Way, also the just normal main sequence star, at least the young and magnetically active, coronally active part of the stellar population of the Milky Way. And then, because our spectroscopic capability and imaging capability, we can study in detail the diffuse emission of the hot ISM in the Milky Way, in the Magellanic Clouds, and in a few nearby extended galaxies. And then we have our time domain aspect, because we go over the same part of the sky many times, both within a day and then within a few months. And so we are hoping and expecting to detect many interesting transient phenomena, including probably hundreds, if not thousands, of tidal disruption events and other maybe more exotic phenomena that we don't know yet. Okay, let me now get back to where I left you on July 13. It was a very hot day, maybe more than 42 degrees in shade in Baikonur. And the Proton rocket was firing. It was around 2 p.m. Munich time. And the launch went perfectly. In fact, textbook launch. This is a description of what happened. That hours the spacecraft was first, and its upper stage were first placed into this parking low Earth orbit, and then the big ignition happened after 1.5 hours from launch, where the upper stage gave the final kick that pushed the spacecraft into this very elliptical orbit in the direction of the L2 point. And a few minutes after separation from the upper stage, we opened the solar panel and we got telemetry almost immediately. It was a very big relief, as you can imagine. This is a plot of the orbit that was delivered. It's a very large halo orbit around L2. I think it's larger than the Herschel one, for example. K1, K2, and K3 represent two major orbit correction maneuver that the spacecraft had to do to insert into this large halo orbit. And in April 16, about a month ago, this blue point marked the completion of the first circle around L2. So we are now in our second orbit around the L2 point. A few words about operations. Of course, operation happen every day. We are at L2, so from Earth we can only see the spacecraft at night, and we get the data down from the Russian large antenna. So mission control center is in Moscow, but operation that regard eROSITA, so commanding eROSITA and downloading the data from eROSITA, happening simultaneously with a team of experts at MP and in Moscow via telephone contact. And we have 2 responsible operators every ground contact, which lasts about 4 to 5 hours per day. This tool works in shift, of course, day and night, weekends. And as you can imagine, we have been affected also by Corona as well. But we were able to move essentially all operation from home. So this is 9 out of our 10 operators shown working during one of the ground session at home. And we are now in the situation in which we can do essentially everything regarding eROSITA operation from home. And the same, of course, is happening in Moscow. Okay, let me tell you then something about the status of the instrument. Few numbers, actually these are already about 10-day-old. We have been now maybe 310 days in space, fully operating the telescope with all its systems for more than 200 days. We have completed maybe now 85% of the All Sky Survey. The ERA stands for the eROSITA All Sky Survey. We had downloaded maybe 150 gigabytes and issued more than 14,000 commands. This is just one simple slide to tell you that all the other instrument units, thermal control of the mirrors, of the cameras, and the CCDs, they are working fine according to our prescription. And the camera themselves, their filter wheels, the electronics, they are operating okay. Let me tell you about 2 hiccups or issues that we have with this camera electronics. So here you see on the left one FPGA, a programmable electronic unit that essentially operates the electronic cameras. And here you see on the right some of the raw frames. Each of them is 50 millisecond exposure. And here you see some in which you see some MIPS, minimum ionizing particle, essentially cosmic ray hitting our detectors. And we have a computer program on board that filters those out. And so in this FPGA, there is quite powerful computers that does quite a lot of pre-processing and filtering in order not to download telemetry down to Earth, a lot of unnecessary information. However, because of the design of this FPGA, they are susceptible to single event upset because they are not completely triple redundant. And so every once in a while, a particle hits the FPGA and make it to hang or to misbehave, and they need to be reset. And we have to do that quite often. So typically once per week, one of the 7 cameras had to be reset. So here you see over the whole history of the mission until end of April, color-coded the amount of good time. So the darker you see, that means that we can use 100% of the time of the camera. When it's light or white, that means that the camera had to be reset, and so we lost some data for a fraction of the time. And here you see that these events, you see these small bars happen for most of the camera and random positioning time. We have had a very big event in February 12, where all cameras had to be switched off because the main computer, the ITC, the controls of the camera, hang itself. There was a bigger scare where we had to go into safe mode for 24 hours. But all things considered, the total amount of time lost due to these camera problems is very small. It's probably of the order of 3 to 4%. So we operate with very high efficiency, in fact. More than 95% of the time is open, so to speak, shutter time, where we get good data. The other problem is light leak. So we have 7 cameras, or 5 out of 7 as a chip on a filter, on the chip that prevent a low energy light to be detected. We left 2 cameras without chip because we wanted to use this camera to study the lowest energies, tens of EV emission. Unfortunately, due to some probably design error, there is some scattered sunlight that comes into the camera depending on the orientation of the spacecraft with the sun. So you see here a time dependence of the angle of the spacecraft with the sun, and these big spikes represent illumination. And here you see the actual image of the camera. So these are very low energy photons of tens, maybe up to 100 EV that you can easily threshold. So you don't, this does not really affect your X-ray domain images, but what it does, by illuminating the camera, it changes the gain, and so it changes the calibration, the energy response of the camera. So it's a bit more cumbersome to use them to do spectroscopy. A few words about some aspect of calibration that we are actually still busy doing. One is Bohr-side calibration that give an idea of our position uncertainty. So I think this was preliminary work. Now we have more than 100,000 matches of eROSITA sources against Gaia quasars. So we can do this quite well as a function of position and time. So our typical position uncertainty for X-ray point sources is of the order of 4 arcsecond, and maybe even a little bit better. This is 1 sigma. And our energy resolution, I don't want to repeat here, is almost a factor of 2, maybe a factor of 1.6, 1.7 better than the XMM Newton. And one word about background. So eROSITA is the first X-ray mission at L2. So understanding the background at L2 is quite important for us. And so here you see in this maybe complicated plot, in black is the entire, in blue is the entire, you collect all the photons in 6 months of all-sky survey, and you plot the spectrum of all the detected photons, source and background, okay? And essentially you can decompose this blue spectrum into a particle background that comes from cosmic rays that hits the detector from all directions, not vignetted through the mirror. And this is the green curve. It's actually measured when we close the filter. We don't expose the camera, we just measure the background. And here you see it. This is actually a factor of 3 higher than the prediction from 2012, from the white book. The prediction would be the solid green line, and the measured value of the background is a factor of 3 higher. And we think we understand this mainly due to the fact that we are at the bottom of the solar minimum, and there is an anti-correlation between sun activity and incidence of cosmic, galactic cosmic rays at L2. So things should improve a little bit as the sun goes into the solar maximum or away from the solar minimum. However, one advantage of being at the solar minimum is that essentially there are no flares. Okay, there are no flares in this particle background. Here you see on the right the RMS of the flux distribution measured when we close the filter. It's only 6%. And here it's an example of an actual observation that we did of a bright AGN, 1H2707, The AGN itself is these blue points, but that's not what I want to show to you. The background is this black, blue, and orange line, thin lines. This is the level of the background measured by eROSITA, and this is a simultaneous level of the background, the same colored line, measured by the XMM-PN and the XMM-MOS. So you see that the eROSITA orbit has a much quieter background, even if the overall level is quite high, but it's very stable, especially when you compare the simultaneous observation of XMM. So this is good news. That means you can quite safely model your background. Okay, I think now I told you enough about problems or issues or successes with the instrument. So in the remaining 20 minutes, I can show you some nice pictures and early results. These are our first light images. You might have seen them. We took them back in October. And actually, here I'm showing the all 7 of them. So we pointed at the Large Magellanic Cloud as a tradition for many X-ray observatories. And actually, we centered our pointing to the supernova 1987A, which is this bright yellowish point source at the center. Here you see the 7 cameras. You see the 7 cameras like different orientation when compared to the position in the sky. And this, of course, is by design. They all have slightly different orientation and slightly different readout, so that when we scan over the sky, we are each readout columns, they don't always span the same direction in the sky. So you can, of course, look at these 7 images, but the nicest is when you combine all of them. And here you see how, and this is again, I should have said, these are false color images created by Frank Haberl and collaborators at MP between, let's say, 0.2 and 4 keV, 3 different energy range. And here you see the beauty of this color. So you see the sensitivity of our spectroscopic cameras that can detect gas at different temperatures, from the mildly hot red to the quite hot bluish structure, most of which are due to past supernova remnants or superbubbles. But of course, you also see a lot of bluish sources in the background. These are distant AGN. Most of them are background AGN. Some of them known, most of them still to be identified. And this is, for a comparison, is the first light image of XMM Newton that also took in the same part of the sky. Slightly shorter exposure. You see the image is a little bit sharper than the eROSITA one, but the difference is with the large field of view, it's clear of the advantage that eROSITA give you. I told you we were pointing to this bright source, and I'm showing here in this inset the spectrum of the supernova 1987A in the LMC, taken with eROSITA CCDs in bluish compared to the XMM spectrum of the same source. As I told you, the exposure is a bit lower, so the errors are bigger, but you clearly see that the eROSITA spectrum is sharper, so you can much more clearly see the line emissions and resolve them better. So this is another of our first light observation that we took over a few days all together with the LMC exposure in October. Of course, this one is not the eROSITA image. This is a ROSAT all-sky survey image of an interactive system of 3 nearby clusters of galaxies, Abel 3391 and 3395. It's actually a triple system. There is a large cluster on the north and an interacting system of 2 clusters in the south. XMM has observed this, but because of the small field of view, we took 3 pointings, looking individually at the northern cluster, the southern interacting system, and then in the middle between the two, there is evidence already in the ROSAT image, here you see, of some excess diffuse emission coming probably from stripped cluster material in this interacting system. And there is even evidence for a group in the middle. So this is the XMM image, and now you see the advantage of using eROSITA in this raster scan mode that I mentioned at the beginning. So this is now the eROSITA image of the same part of the sky. This is a genuine single band X-ray image in the most sensitive part of our CCDs between 0.2 and 2 keV, with just some Gaussian smoothing. You see, of course, the clusters, plenty, of course, of background AGN. The typical exposure in any average exposure of this image is about 20 kiloseconds of eROSITA. But you see quite a lot of extended clumps, and many of them now we know are at the same redshift of this interacting cluster system. So we see the inflow of clumps and the large-scale structure forming into this interacting cluster system by having this large field of view around them. These are also our first light images. On the right, on the left is a false color image where you see the different colors of the background AGN, and now on the right, the same single band, now not the same, between 0.4 and 3 kV, but now with wavelet filtering to enhance the emission from the gas in between these two clusters. Okay, another nice image that is coming up, but it's also a nice story, because this is an image of a supernova remnant, Puppis A. This was taken with a sounding rocket launched by MPE in '79, so more than 40 years ago, and it was at the time probably the first so its first color image, in the sense the first time you could detect soft X-ray photons at different energy and build a color image with them. And in fact, not only was the first time you can do this color imaging, but it was at the time the first actually X-ray color monitor that there was at MP, where you can actually see the different colors on your screen. And of course, we went back to the same source with eROSITA. It's a very bright supernova remnant. So in 60 kilosecond exposure, you get beautiful images that reveals a lot of detail of these supernova remnants. And also, of course, the different colors representing different temperature of emission of the components of the supernova remnant. Okay, we took quite a lot of other deep exposure in our calibration phase, a few big clusters to calibrate our effective iron vignetting. On the left, cool core cluster, quite well behaved, roundish. On the right, an interacting system. These are all about 70 kilosecond exposure. We had the raster scan image over almost 5-6 square degrees around the Coma cluster. These are led by Eugene Shurazov at IKI. And on the right is the same Abel 3266, now in a very nice image done by Jeremy Sanders at MP, that you can see some very nice structure in the ISM, maybe some filaments or bubbles. We still don't know exactly what they are. We don't see strong X-ray or strong radio emission associated to this cavity, but just to show you how nice this image can be when you observe deeply with this very large field of view. Okay, most of the time during our calibration and performance verification was spent, well, not most of the time, but the largest chunk of allocated time during the PV phase was spent on a mini survey that was designed to give us a preview of what the eROSITA all-sky survey would look like at the end of the 4-year program. So we observed 140 square degree in an equatorial field with a lot of multi-wavelength information already available for about 2.5 kilosecond in each location, for about 300 kilosecond in total. So maybe four days of observation. And this is the exposure corrected image in the 0.5 to 2 kV band of this EFETS field. So what you can see there, you can see that the X-ray image themselves, just by resolving out the extended emission in clusters, can be used to pinpoint where clusters are. So simply by looking at X-ray image, we can detect maybe 430, 440 clusters, or at least cluster candidates. You can then go and look at the imaging, optical near infrared imaging. For example, there is very deep Subaru data in this field. And so you can use photometric redshift technique or red sequence finder technique to identify the counterparts in this cluster. So more than 370 have been optically confirmed, spanning redshift between 0.1 and 1. And this is just an illustration, not more than that, of the luminosity versus redshift distribution of these 370 identified clusters, showing that we detect a few objects above redshift 1, which is very important because they will give tighter constraint to cosmology. And of course, there is a lot of work going on right now in measuring temperature, masses of this cluster using weak lensing, more than what I can tell you, but this is an illustration of a relatively bright object at high redshift, high for cluster standards, so redshift 0.6, 0.57 cluster. It's a massive object, almost 7 times 10 to the 14 solar masses, but here you can see the surface brightness profile that we detect with eROSITA, and we can resolve it. We can clearly see the profile above the PSF, which is this blue dotted line. So we resolve the cluster almost up to 500, where we start going into the background. So then we can measure temperature, but this is important because that will allow us to derive property of the ISM, assuming hydrostatic equilibrium. And then using the weak lensing, we can calibrate these mass measurements. let me get back to this image. Of course, only 450 clusters, but there are many more sources you see in the sky. There are about 25,000 point sources detected. So just by the sheer number of sources that we detect, this 4 days eROSITA observation experiment is already now today the largest contiguous X-ray survey ever done. We choose, of course, a place in the sky where there is a lot of existing ancillary information. So combining public spectroscopic data and some data that we took as part of the SDSS SPIDERS program, there are more than 6,000 spectroscopic redshift for mainly for the AGN that you see in this field. And here I'm showing you, for those more interested in the follow-up properties, the optical magnitude as a function of X-ray flux for all the point sources we detect in this EFETS field. And the red objects are those for which Gaia tell us there is significant proper motion, more than 4 sigma. So these are, of course, stars, and they tend to live, as we knew, at the bright end, the optical bright end of the distribution. But most of the objects, as you can see here, these are AGN, and they have median optical magnitude about 21st. So they are definitely reachable with 4-meter telescope like FORMOST, and even with smaller telescopes like SDSS. Among the interesting things we have found by looking at the AGN in this field, we have rediscovered, but this time blindly, a redshift 5.8 known quasar. This was a quasar for which there was already a Chandra detection, but it was detected in X-rays as a follow-up. And so if you want, we just blindly detected in our EFETS catalog. So this is the highest redshift X-ray blind detection ever. The previous record holder was maybe redshift 5.1 or so. And we have a number of interesting candidates of redshift greater than 4.5, 35 of them just by looking at their classical color, optical near infrared, and X-ray color properties. The green one is the redshift 5.8 quasar. These objects are consistent with the tracks of obscured AGN at redshift 4.5 to 5. There are a few for which we get very good infrared imaging, and this is one of the most promising ones for which the photometric redshift very clearly indicate redshift 5.4. We may have 4 or 5 of them, and we are trying to get spectroscopy, and most of the big optical telescopes right now are shut because of Corona. So it will take us a little bit longer, but there is interesting promises for exploring high redshift universe with this X-ray data. Of course, there are stars in the field, and there are a group of, mainly led by Jürgen Schmidt in Hamburg, which are interested in these coronal active stars. Here you see the Gaia color, blue minus red, versus bolometric luminosity. Essentially, this is the HR diagram for all the eROSITA detected coronally active stars. Essentially, you see X-ray emission throughout the main sequence, color-coded by the X-ray luminosity. And this plot shows instead, as a function of color, the X-ray to bolometric luminosity ratio, which is itself an indicator of rotation and youth in this star. So a lot of interesting stellar population study to be done by exploiting the synergy between Gaia and eROSITA. Okay, now let me tell you what we are doing since we started the All Sky Survey in December. This is a projection in the sky of the All Sky Survey photons, as simple as they are. This is an exposure-corrected image in the 0.6 to 2.3 keV band, so nothing more than just slightly smoothed. And here you see that we have covered mainly 80% of the sky. And as Trumper used to say at the time of the Rosa All Sky Survey, here I'm just illustrating with a few examples the benefit of the unlimited field of view, or when you have this uniform exposure over a large area of the sky. Here I'm just picking up a few examples of just image that you can retrieve from your HIPS maps of an extragalactic field. This is the Shapley supercluster. So I'm showing you an example of fields of few degrees wide. So here you see the clusters of the Shapley supercluster. Here you see a very nice supernova remnants. And here you see another supernova remnants, and this very beautiful circle. This is, when you talk about serendipity, this is a dust scattering echo coming from a bright X-ray binary that went into outburst last year. And you can pick up the echo. In fact, there are a few more circles, and they trace different dust cloud along the line of sight between us and this X-ray binary. This is now a view of the galactic center on the left and the inner part of the galactic plane. And I'm just going to give you just an overview of about 1/4 of the galactic plane, just taking, as I told you, the eROSITA whole sky survey images and projecting it into the sky. You will see a lot of nice diffuse structures, beautiful supernova remnants, bright extended sources and bright point sources. Again, the dust scattering halo, and this is now closing onto the Carina Nebula here at the center of the image. So it's just about 1/4 of the galactic plane, but plenty of nice data to look at. One other aspect of what we have been doing in the Whole Sky Survey is to look for variable and transients. So, of course, we are scanning the sky for the first time, so we can compare either with the Rosat Whole Sky Survey, which, however, is quite brighter than the eROSITA flux limit, so we only detect the tip of the iceberg. But over time, we have been alerting the community for different sorts of transients. Many in the LMC that we go over often because it's close to the ecliptic pole. We have had a few bright galactic sources. Even we caught GRB, X-ray afterglow, and in blue a couple of bright transients of unknown origin, for which we still don't know what is the right counterpart. And I want to focus on this last one. So the green are nuclear transients, so transient clearly associated with nucleus or nearby galaxy. And we think these are probably good candidates for tidal disruption events. This is one that we found maybe, yeah, it's on May 7th, so it's less than 2 weeks old. That's the eROSITA position. It's a very clearly and consistent with the nucleus of a bright galaxy. The spectrum of eROSITA over 1 day visit in 200-second exposure is very soft, essentially consistent with a black body of 86 eV electron volt, which is consistent with what you expect from a nascent accretion disk around from tidal disruption events. And this is a factor of 90 brighter than the XMM upper limit that we have from the same location in the sky. So clearly all indication about tidal disruption events, but then the optical light curve of the system is very puzzling. Actually, there was a very bright, with some evidence of cooling, maybe that looked like a supernova event. These are now ZF light curve for this source in February 2019, and now there is a rebrightening that is really very rare, or maybe unknown of in supernovae, happening now. And we caught the source close to this peak of the rebrightening, so we are now triggering follow-up in X-rays, optical. So stay tuned to see what these interesting sources will be. Okay, a summary about the status of the Whole Sky Survey, and actually I'm about to close my talk. So as I told you, we cover more than 80% of the sky. I think we counted about 300 million good, well-calibrated photons in the energy range between 0.12 and 4 keV. We have maybe a factor of 10 more valid events, but most of them are noise, either low energy or high energy. But so the sky is covered with relatively uniform exposure, about 200 seconds, apart from the region close to the ecliptic poles, where we scan more often. As I told you, the background is higher than expected, but very well behaved. So there have been no background flares. That means that also coupled to our ability with flexible mission planning to recover from camera problems, as I will show you the one that happened in February. So we could fill the gap that was produced in the sky, but not having 2 days of data. And so as of today, we are so the Whole Sky Survey we completed as of today has no gaps. So we hope that in the last month we don't have any nasty surprise, and we'll be able to show to the world the full sky picture of eROSITA in late June. We're finding many transients. In fact, many more than what I told you with ATELs. A lot of them are flaring stars, but there is right now a lot of work going on internally in the team to understand how we should do a vetting process, so not to be too overwhelmed by the number of alerts that we have internally, with the idea of streamlining this alerting process to be able to alert the community of as many interesting events as possible. So the first very early days attempt of building a catalog with our existing software, which works well, but we are still in the process of calibrating some detail of the instrument. It tells us we detect about 400,000 sources only in the one hemisphere we are looking at, the German team is looking at. So the prediction is that in less than 1 year, we will discover more than the total number of sources that have ever been cataloged by all previous X-ray missions in the history of X-ray astronomy, which are about maybe 1.2 millions, if you take all together the Chandra, XMM, Swift, and Rosat catalogs. So the summary of the summary, SRG was launched in July 13 of 2019 from Baikonur, and it's now in its large halo orbit around the L2 point. And the All-Sky Survey has begun in December 13, and we hope it will continue for 4 years. The performance of the instrument, at least of eROSITA, but also ARTEX-C, is behaving as expected. So, but in our case, we confirm our design performance. We have very good image quality, as I've shown you. Spectral resolution of the cameras is excellent. Despite all the issues at the operation level, we are observing with high efficiency. And I think we are on course to match our global survey prediction of detecting more than 100,000 clusters of galaxies and 3 million AGN, probably significantly more than 3 million AGN. As I told you, there are issues, as always. In fact, when you build this kind of instrument, we have optical light leak in 2 out of the 7 cameras that essentially degrades the soft spectral resolution, but have very little effect on imaging capabilities or broadband imaging. We have small data loss due to unstable behavior of the detector electronics. There could be some mitigation strategy of an updating of the firmware, but this requires a lot of testing on ground and will not be done before the next 6 months or so. And we have reduced hardband sensitivity because the higher particle background, higher than at least the expectation pre-launch. In terms of the data, the eROSITA's API instrument, if you want to work with our proprietary data, you have to collaborate. You should collaborate with us. But we are going to release in different batches our data. So the PV and calibration data, including the effects field I've shown you and some of these beautiful cluster images, will be released in early 2021. So typically 1 year after they have been taken. And calibration have been consolidated. And then we will release the All-Sky Survey data after a 2 years proprietary period. And so we will release the first All-Sky Survey in 2022, the first 4 combined All-Sky Surveys, catalogs and images and photons in 2024, and then the final ERAS-8, so the 8 All-Sky Survey combined in 2026. And as I told you, in just about 3.5 years, there will be, or even less, there will be an announcement of opportunities for the community to use a large fraction of the eROSITA time available, and there will be periodic calls, and hopefully we will be able to continue operating the telescope for many years after that. So that's bring me to a close. I want to thank you very much and thank once more all the many people that over the years have been working on the instrument, on the mission, on the software, on the data, on the science, and this is probably just an attempt to list many, if not all of them. Thank you.
Fantastic. Thanks very much, Andrea. I probably better let that finish scrolling before stopping the recording. Ah, there we go. It has stopped.
Sorry.
That's okay. So